My name is Juan Alonso. I'm a professor of Aeronautics and Astronautics at Stanford University. And in general, my research interests are well aligned with the design of new and unconventional aircraft configurations that one day may realize substantial fuel savings compared to what we have today. I'm also interested in designing airplanes that don't use fuel at all, and that might become powered by electrical means, whether they're batteries or hydroelectric systems, and that's another pathway towards a very green future for commercial transportation. So in 2010 and 2011, we put together some forecasts of fuel efficiency improvements for the year 2020 and 2030. So it was a view 10 years out and maybe 20 years out. And for 2020, so 10 years out, we were hoping to have a reduction versus the year 2005 of about 30 to 33% in some relatively aggressive technology scenarios. It is the case that we've been improving at less than 1% per year compounded. So if you think we are 3 years away from 2020, that'll be a total of 15 years from 2005. We will only have achieved on the order of 15 to 17% of those improvements, whereas we wanted almost twice as much. So there is some room and there's some opportunity left on the table for aircraft to be designed with a slightly more advanced technologies and redesigned from a clean sheet in order to get closer to those goals that we have set up. Well, it's a combination of two things. First, the goals we set up were certainly aspirational in the sense that they were pushing the technology quite far, within the realm of the possible, but certainly something that was going to carry significant technology risks and additional costs. The aerospace industry has been traditionally, well, for good reason, has been relatively risk-averse. And I think that's the main reason all of the technologies that could be available are not necessarily introduced into the next generation product all at once. And therefore, we realize smaller improvements than what we could get, but the risk for the companies is significantly lower. Well, so tied to the low tolerance for risk by the aerospace industry is the fact that instead of taking an airplane from one generation and redesigning it completely for the next generation, we tend to take an existing airplane and make incremental improvements in its configuration. So what we call a clean sheet design is not necessarily something that you see from generation to generation of aircraft. Substantial opportunities beyond the introduction of technology that I discussed before can be found by simply changing the configuration itself in this clean sheet design aspect that we talk about. And it's not just the configuration, it's also the engine. So you can realize larger improvements. So of course, you leave some things on the table when you don't realize clean sheet designs from generation to generation. Normally, because of both technology and economic constraints, an airline will only buy a new generation of an existing airplane if the fuel and direct operating costs are probably about 10 to 15% lower than the previous generation, right? So normally commercial aircraft companies and engine companies develop these systems so they can at least get that much and they can motivate some of the customers to buy, the airlines themselves, to buy one of these new airplanes. The difficulty there is that we are using sort of technology and iterations or minor changes to existing configurations in order to meet that customer demand. Clearly, we're leaving on the table some potential reductions in fuel burn if we started with a clean sheet of paper and redesigned an airplane from scratch. What do I mean by a clean sheet of paper? Well, one that incorporates the knowledge acquired from previous generations of aircraft, but at the same time allows more freedom into the shape of the configuration and the parameters for the engine cycle, such that you can specifically tailor for the level of technology that you have today, or tomorrow, or the day after, and for the type of knowledge that we've been developing as to how to integrate these technologies. So clean sheet simply means unencumbered by knowledge and experience that has come before. And that means that you don't choose the same parameters with minor tweaks, but rather you learn from what you did in the past and you take larger leaps of faith in terms of figuring out what the configuration might look like. An Airbus A320neo, for example, is an incremental change over the Airbus A320 that we're flying in today. A Boeing 737-900 is an aircraft that is an incremental change over the Boeing 737-800 that we're also flying around today. A DC-3 is not an incremental change from the previous generation airplane, but rather is a complete departure from what had been done before, and therefore we call it a clean sheet design. In the future, we would like to see clean sheet of paper designs that are departures from existing Airbus A350s or Boeing 787s. And by that we mean aircraft that may have much different configurations, better propulsion system integrations, and even electric propulsion systems. We would call that a clean sheet design because it leverages the knowledge that's been acquired from many earlier generations of aircraft, but it takes a substantial leap or a significant departure or a significant change from the previous generation airplane. And in doing so, you were able to achieve some significant reductions in fuel burn that wouldn't have otherwise been possible. What we do normally is to design an airplane that is an increment from the previous generation. If instead we use a clean sheet of paper design, where we allow ourselves to change both the aerodynamic shape of the configuration, the engine parameter cycle, and the actual structural configuration, we can discover new areas of the design space using this clean sheet of paper design that can lead to more substantial fuel burn improvements. While our aspirational goal in 2010-11 was to get to about 33% reduction, and we may have only realized about half of that much, with this clean sheet of paper types of designs, you can get closer to that aspirational goal and perhaps get things or airplanes that are about 10% more efficient. And 10% is a lot to leave on the table, particularly when the environmental impact of commercial aviation is concerned. I mean, in terms of fuel efficiency, I think DC-3 may be one of the most advanced aircraft compared to the previous generation, and I would say representative of a clean sheet of paper aircraft. Look at the airplanes right before the DC-3, which were mostly biplanes with structural designs that were quite different, with engines that were not potted, with landing gears that did not retract partially. So I think the DC-3 for me represents an aircraft that was a leap in performance and a leap in fuel burn efficiency because of a number of technologies that came together that allowed the aircraft designers to say, no, we're not going to design an airplane that is exactly like the last generation or a small tweak from it, but rather we're going to conceive it from the ground up from a complete sheet of paper design, complete clean sheet of paper design. The DC-3 represented a radical departure from the way in which aircraft had been designed before. So the improvements in efficiency of the engines, the structural efficiency improvements, and the aerodynamic efficiency improvements led to, I would say, approximately 30 to 35% better fuel efficiency than the previous generation. This was used not just to reduce fuel efficiency, so to improve fuel efficiency, but rather to increase the range and the payload capacity of this particular aircraft, which in the previous generation have been somewhat deficient for potential use in commercial air transportation. Aircraft have been optimized quite a bit, and while there's still room for improvement, it's probably not technologically possible to improve at rates that approach 8% per year. However, being under 1% per year is also unacceptable. I believe that we can improve the rate of performance of an aircraft that's a commercial aircraft over the years at levels that are higher than 1% per year. How much we can push that improvement in percentage per year, it depends on how many technologies get introduced and how confidently we can do that in a product that can be successful. But I don't think that the estimates of performance that have been done by ourselves in that 2010-2011 study or by other prestigious institutions like NASA which look at the year 2035, 2040 and have substantial decreases in fuel burn, like 50% reductions, I don't believe those are out of scope. With significant technology investment, with clean sheet of paper designs, and with new concepts for the aircraft configurations that carry passengers around, you can approach those numbers, leading to significant improvements in the commercial aviation environmental impact. For me, when I look and extrapolate to 2050, I'm mindful of the fact that that is almost 35 years from now, and it's very hard to predict exactly what these airplanes look like. But by 2050, you'll see radically new and different aircraft configurations. No longer the typical tube and wing or fuselage and wing type of configuration, but more advanced configurations that may have extremely high spans, truss or strut-braced wings, potentially blended wing bodies. What you will see as well is a much closer integration of all the technologies than you see today. The engines won't be two power plants hanging off the wings that are integrated as an afterthought, but rather will be embedded into the airframe. The structural efficiency of the designs will be much, much larger because of the materials and the specifics of the structural configuration that are chosen. The aerodynamics themselves and the configuration will be tailored in order to improve the lift-to-drag ratios, which are now around a value of 20 in the cruise condition, to values that could approach 30 to 35. So all of these things together conspire to put together a vision of what these 2050 airplanes might look like that end up looking quite different from what we have today. If I could add one thing too, in 35 years from now, I would imagine that a number of the shorter range aircraft, so typical regional jets, etc., could also have migrated to a full electrical power plant, bypassing the need for the use of fossil fuels, and therefore having a tremendous impact on the environment. The final thing I would tell you is that for the mid to large size aircraft, which are less likely to be powered by electric power plants, you may see a combination of standard fuel and also alternative fuels that may have much lower life cycle carbon costs than the typical fuels that we extract from the ground today. Yeah. So there's several technologies that are ripe for use, particularly in medium and large size aircraft. I would like to see much larger bypass ratio turbofan engines benefiting from the use of alternative fuels in the next generation of aircraft. I think that's likely to happen. Much more closely integrated engines into the airframe such that there are no negative impacts of the much larger engines themselves. And I think I'd like to begin seeing laminar flow, whether it's natural laminar flow or hybrid laminar flow, in significant portions of the aircraft, not just in the cells, but also the empennage, so the vertical and horizontal tail, and possibly in the next 15 to 20 years begin to see more penetration of laminar flow in the wings of these commercial transports. An additional technology that is likely to find its way into the design of midterm airplanes, those that may be 15 years away or so, is much more intelligent use of composite materials. While we have composite airplanes today, the structural design of those airplanes simply use a stronger and lighter material as if it were aluminum. So often these airplanes are called black aluminum airplanes. That means that the design process for the structures in these airplanes are following rules that were developed for aluminum 50 years ago. I think while the materials won't improve substantially over the next 15 years, the use of those materials in more intelligent ways will lead to significant weight reduction in the structural design of future aircraft, and that will also contribute, together with aerodynamic and engine improvements, to much reduced fuel burn. Technology for composites has been around for a long time, but you have to understand in the aerospace industry, the maturation times for these technologies are long. So in the early 80s, 1980s, people were looking at composite technology, and the first real airplane that has substantial composite structure is the 787. So there's a difference of about 30 years between the introduction of the technology and its practical use in a commercial airplane that you and I can fly on. However, as I mentioned before, you're actually using these composites as if they were solid pieces of aluminum. Composites have a key capability that must be exploited in order to make lighter airframes that are more fuel efficient. That capability is the following. When you put together a composite, you're making it out of thin fibers that can be oriented in any direction that you want. And if you exploit the tailoring or the orientation of those fibers at various different layers that make up the composite, you can actually get much better structural properties than if you simple-mindedly put them together in the black aluminum way that we were talking about. So updating some of the design rules, learning more about how to optimize these composite layouts can lead to structures that carry the same loads that you see in a normal airplane, but at the same time end up having much higher structural efficiency, meaning they can carry those loads for much lower weight. And that's a fundamental part of the range equation of any airplane that leads to the amount of fuel that is actually burned and can reduce substantially the fuel burn of these commercial aircraft. On the one hand, governmental institutions need to provide the seed funding for the basic ideas that eventually, 10, 15 years later, develop into technologies that an aircraft manufacturer may want to consider as a candidate for introduction into a new airplane. So that original seed funding and carrying it to a point where industry can begin to see the value of that technology if introduced into a product, I think it's a direct governmental responsibility. Institutions in the United States and abroad, like NASA, DLR, ONERA, JAXA, have as one of their main missions to perform these types of tasks. And given enough funding from the government, they're doing a great job. The second part of the answer is that government also has a key role in regulating the aircraft industry. We have never had a fuel burn standard until the CO2 metric was developed by ICAO in the last couple of years. So there is also a secondary role where judiciously government institutions and international institutions can have to set the bar high enough such that the standards are not just merely catching up or allowing every aircraft that exists out there to be able to fly legally, but rather so the technology standards are forcing the adoption of some technologies in a responsible way. Responsible means not setting the bar too high such that the risk involved will be so extreme that no responsible aircraft or engine manufacturer will develop a new product that introduces these technologies, but also not setting it too low so the people who supply these technologies and these aircraft are complacent. So government has a strong responsibility in deciding where to set those standards and how to adjust them over time in order to both do the proper incentivation of the industry itself, do it in a manner that can be risk managed appropriately, and I would say most certainly in a way in which the overall benefit to society outweighs the costs of introducing these technologies. If I were to tell you something else about that last comment in terms of the governmental role in setting standards, government has an obligation to look for the well-being of the entire population of a country or of humanity as a whole. And that means not just one source of emissions, but many different sources of emissions. So the benefit to society from the entire set of reductions in emissions compared to the costs of producing those emissions is also a consideration that government would have to take into account when imposing standards in different transportation or non-transportation sectors of the economy. I have been somewhat disappointed. I'm an academic, so I have to caveat this response by saying that I don't live on a day-to-day way with the risks that aircraft and engine manufacturers live with, which are quite significant. But I have been a little bit disappointed that the standards have been mostly technology following standards rather than technology forcing standards. I have to say I'm also not one in favor of outrageous technology forcing standards because I do think they may be either unphysical, unrealizable, or they may stifle innovation. But I would like to see government doing a setting of limits for the standards that it's a bit more on the forcing side than what we've seen so far. The way our economy is set up, private companies are there to benefit the shareholders. So in some senses, their allegiance is to maximize the profit of the company for the benefit of the shareholders over the long term. I think most companies in not just aerospace, but other transportation sectors have been very focused on the near term, on how many airplanes or cars can be sold in the next few years, right? I think if you start taking a longer term vision of the actual profits of these companies, you start believing that having a responsible posture in terms of environmental impact is going to be really much more valuable to the company overall. So I think industry is beginning to realize some of that, and it's working against some real serious risks of introducing technologies before its time that can cost billions and billions of dollars to the company. But I would like to see more internal realization within industry of the fact that in the long term, introducing some of these technologies, further reducing fuel efficiency beyond what is being done today, actually is not just corporate responsibility, but it's good for the bottom line of the shareholders. The main message that I would like to send is that we have technologically feasible solutions to do better than we're doing today. The reason we're not implementing some of those technological solutions is that there is significant risk involved in going from a product to one that is a clean sheet design and is therefore radically different. I think the key is in ensuring that we can minimize the risk of introducing these technologies and that at the same time we can reduce the cost of putting these new technologies on aircraft. If we can figure out how to do those two things, we will find the rate of improvement of fuel burn in the commercial aircraft fleet accelerate rather than decelerate in the next few years. And that's the type of future we would like to see at institutions like